Current methods for making NMC battery materials requires high calcination temperatures, long processing time, and consume a lot of energy. Additionally, poor precursor mixing in traditional methods often leads to compositional non-uniformity, resulting in structural degradation and reduced cycle life. As a result, the batteries do not last long, and their performance drops faster. NMC 811 provides high energy density due to its high nickel content, but it still suffers from structural instability, cation mixing, microcracks, and capacity loss during cycling. One way to improve this is through doping, by adding small amounts of other elements to strengthen the layered structure. PowerMIX, which uses titanium and magnesium codepants, helps stabilize the material in a lower energy high-performance solution. In this study, we aim to synthesize PowerMIX, also known as titanium-magnesium-doped NMC 811, using hybrid mechanochemical thermal method. Second, we target a pure single-phase layered hexagonal structure. Third, to achieve stable electrochemical performance, with higher initial discharge of 190 mAh per gram. And finally, reduce cobalt content for better energy efficiency and scalable production. The hybrid mechanochemical thermal synthesis method enables efficient precursor mixing and controlled phase formation, resulting in improved structural uniformity. Through dual doping with titanium and magnesium, the layered NMC structure is further stabilized, as titanium enhances mechanical robustness while magnesium helps suppress cation mixing. This combined approach lowers overall energy consumption during synthesis and ensures uniform particle distribution, ultimately reducing cation mixing and enhancing the electrochemical performance of the material. PowerMIX methodology. The cathode material was synthesized using a conventional solid-state method. Commercial NMC 811 precursor powder was ball mixed with 2% titanium nitrate to give Ti-doped sample, 2% magnesium nitrate to give Mg-doped sample, and incorporation of 2% titanium nitrate and 2% magnesium nitrate to give a Ti-Mg co-dopant sample. Lithium hydroxide was added at a 1.101 ratio to compensate for lithium loss during annealing. The mixture was ball milled at 400 revolutions per minute in 4 cycles of 5-minute milling and 5-minute rest, then annealed at 750 degrees Celsius for 15 hours under nitrogen. The final product was manually ground and sieved to obtain a fine powder. In Figure 1, all Ti-doped, Mg-doped, and Ti-Mg dual-doped NMC 811 samples remain isostructural with pristine NMC 811, maintaining the hexagonal layered R3M structure with no impurity phases, which helps lithium ions move efficiently during intercalation-deintercalation process. The increased RIR values after doping, highest in the dual-doped PowerMIX sample 1.22, confirm successful Ti and Mg incorporation and reduced lithium ions nickel-ion cation mixing. Morphologically, PowerMIX shows smaller, more compact particles than pristine NMC 811, whose thin primary particles evolve into polyhedral clusters after annealing. Elemental mapping indicates uniform distribution of all transition metals, confirming good homogeneity. Electrochemically, pristine, Ti-doped, Mg-doped, and PowerMIX samples show initial discharge capacities of 182, 179, 185, and 192 mAh per gram respectively. The PowerMIX sample also gives the best capacity retention, 90.5 versus 62 for pristine after 20 cycles. Its improved cycling stability is likely due to enhanced structural ordering, reduced cation mixing, and its compact uniform particle morphology. PowerMIX effectively stabilizes the NMC 811 structure, reduces cracking, and improves battery lifespan. Benefit contributions in SDG alignment is PowerMIX supports cleaner and more efficient energy storage, promotes sustainable battery innovation, reduces waste and energy use in production, and helps lower carbon emissions in clean energy systems. While to society, it enables safer, longer-lasting batteries for EVs and renewable energy, reducing e-waste and long-term costs. Commercially, it offers high performance, lower production cost, and scalability for EVs, solar, and grid storage, with strong potential for licensing and IP advantages. This work on the synthesis of NMC precursors, selected dopants, and their effects on electrochemical performance has been published in the journal Helion and received copyright in 2025 under the title Nickel-Rich Lithium-Nickel-Manganese-Cobalt Oxide Cathode Materials, a review on the synthesis methods and their electrochemical performances. In conclusion, PowerMIX yields stable titanium-magnesium co-doped NMC with a capacity around 180 mAh per gram. Its energy-saving and scalable production process ensures practical applicability, while its enhanced structural stability and performance make it ideally suited for use in renewable energy technologies.